Welcome to our first online lab session. Today we will try to implement basic optimization basic problems we have studied. Let's try to focus on a very simple problem for which we already know the solution. Minimize x minus 1 whole square. It's a very dummy problem. So if you plot like this, so here is a sketch and we know that the minimum value of this function is at x is equal to 1 here, and the minimum value is 0. Now let's try to see how to implement this in Python. Here is our Jupyter based console, and the package which we will be using is called CVXPY. CVX for convex and Py for Python. So this package is actually specific to Convex Optimization, CVX package. It has extensive help available online. I will share the link with you all. And let's import this as CP. Okay. So now this function has been, this particular library has been imported. It's a very simple library to use. So now first thing we need to identify is how many variables are there. So this is simple one-dimensional problem. So we just have one variable here, x. So we'll define that variable like this. X equals cp dot. So when you press cp dot, you press the tab. These are the different type of functions which are being supported under this convex optimization package. So the function we need right now is variable definition. We want to define a variable. So capital V A-R-I-A-B tab. So here is the variable, and we will do nothing but just have the brackets like this and shift enter. We got it. So now x, if you write here, it is a variable, one-dimensional variable. Okay. See, here you have to differentiate between the variables you usually have in Python which take numerical values. This is a little bit different variable. It is sort of algebraic quantity. You will see what I mean by that. Now what is our objective function? It is x minus 1 whole square. So we need to define the objective function. It's very simple. Suppose I write obj is equal to, now how to define objective function? So cp dot, what is our objective? We want to minimize x minus 1 whole square. So there is a function which starts with capital M, M-I-N, you see, minimize. Okay, and then in between the brackets here we need to write the function. So what is the function? It is x minus 1 whole square. So x minus 1 whole square. Run it. Now objective has been defined. This is the objective function. You see, it has automatically diagnosed that it is a convex function, of course, x minus 1 whole square. It is a non-negative function. We know that x minus 1 whole square is always greater than or equal to 0. Now after this, let's have no constraint right now. Okay. So after this, in Convex Optimization package CVXPY, we need to now define the problem. So let me write here problem is equal to cp dot. Now we have a function problem. What to do? Solve this objective function. Solve this objective. So problem bracket objective. Okay. So now we have defined the problem. We want to solve it. So to solve it, write this problem dot, there is a function solve. Just run it. Okay. So what we got here directly is 0.0. This is basically the minimum value of function, which we already know that the minimum value of this function is 0, 0. Now if you want to know at which value of x this minimum value is attained, so just write x dot value. See here 1. Okay, we got this value as 1, and we know that the minimum value of this function, is occurs at 1. Now let's change function so that we get some different taste. Let's suppose we want to minimize x minus 3 whole square plus 2. So can you guess what will be the minimum value of this function? You see how we'll plot it. At x equal to 3, the value of function is 2. So somewhere here, and this is 3. Okay, let me draw it. Function will look like this, that at x equal to 3, the value of function is 2, which is the minimum value. Let's check. We'll change. So we'll go back to, first of all, the objective. It is now x minus 3 whole square plus 2. Okay, so now objective has been changed. Now we need to go back to the problem statement. We update the problem statement, cp.problem objective. Now we need to solve the problem. Problem dot solve. See, now when we solve the problem, we got the answer 2. Let's name a variable y. Now this y contains the value 2, and exactly at 2 we know that the minimum of function occurs. And what is the minimum value of function? So that we can find here, I mean, at what value of x the minimum occurs. So you can write like this. So 3, fine. So at 3 we get the minimum value of the function. So this is very simple to use. Let's now do some different function. Okay, let's check the minimum value of this x square minus 2x plus 4. So we need to change the objective here. So it is x square, then minus 2x plus 4. Fine. Then we need to define the problem like this, problem cp.problem. Fine. Then we need to solve the problem dot solve. Okay, so it shows that the minimum value is 3 and which occurs at 1. Let's check. So here is the Desmos plot of x square minus 2x plus 4, and the minimum value is here. You can see that it is exactly here 3, and the minimum value occurs at 1. It's otherwise also very easy to verify, because you can write this as x minus 1 whole square plus 3. We know that its value is minimum value is 3, which occurs at x equal to 1. So this way you can basically change the objective function, any of the functions. You can have even non-convex function, but you know the solution will not be unique. For convex functions, this is a very good solver. You can use it for any complicated convex functions. Now let's try to put constraint into it. Now let's add a constraint here. Let's say that our constraint is that x should be greater than or equal to 5. Let's see what will happen. First of all, we want to see how to add the constraints. So let's go back to the console. For constraints, you need to define them like this. CONS constraints equals, so then square bracket, and I want to have x greater than or equal to 5. Fine, that is it. Then close the bracket. So we have defined the constraints. Now how to incorporate these constraints? Remember that we have defined a variable problem like this, cp dot problem. Here we had objective. Now we will add also constraints. Okay, now when we will execute the function problem dot solve, it will now execute it along with the constraints. You see the value changed now. The optimal value for this constraint x greater than equal to 5 is 19, rather than what used to be earlier 3. And what is the value of x at which this takes place? It is 5. And it's quite obvious if you go to this Desmos figure also. When you have a constraint, suppose here is the 5, this is 4, this is 5 here, and at this moment this is the minimum value you can have. So let me just try to pick. Okay, so here is a 5, and at 5 you can check that the value is 19 here. Okay, or if you want to see here, So it is x minus 1 whole square plus 3, and you want x should be greater than equal to 5. So the minimum value will occur at x equal to 5, which is 5 minus 1 whole square, which is 4 square plus 3, which is 16 plus 3, which is 19. So the value of function at x equal to 5 is 19, which is the minimum value. So this way we can incorporate the constraints also. I would like to keep these videos short so that it is very easy for you to comprehend it. So in next video we'll see further how to solve multivariable convex optimization problems using the CVX package. Thank you.